So today we're going to talk about friction. We've already done problem solving that have friction in it. Friction is a very common force, but we haven't actually talked about the nature of friction. Okay, what can cause it? What can influence it? Okay, things like that. So much of what we do is designed around either maximizing friction in some cases, or in other cases minimizing it. A lot of minimizing it because friction obviously affects efficiency. We want to do things as efficiently as possible, use as little energy as possible to do jobs. So finding ways to reduce friction is pretty important. But there are also times where we want to maximize it. Like very soon we will be driving on icy roads. Okay? And if we want to drive safely, we need to A, go slower, and B, okay, have ways to increase friction. All right, so we'll talk about the nature of that here. Now, when it comes right down to it, friction is present anytime two surfaces are in contact with each other. Okay, anytime they're in contact with each other, right? And it is them trying to slide past one another. Right? What influences that is the nature of the two surfaces. Okay, if they are very slippery surfaces, there will be very little friction. They'll slide past each other very easily. Okay, if they are very high friction surfaces, then it will be difficult to make them slide past one another. All right, everyone kind of follow me there? Okay. All right, let's talk about kind of what causes this. So there's two types of friction. Let's talk about that first. Okay, there's static friction and there's kinetic friction. Okay, so static friction is the kind of friction that is present when the objects will not slide. Okay, so they won't slide if there's static friction. So basically, in a static friction situation, there is no movement. Okay, so in a normal situation, when I'm walking, there is static friction between my feet and the floor. Okay, my feet don't slide. I can push on them and they'll push me forward. Okay, now if there is friction, then I could be sliding all over the place. Right? A prime example of this is in curling. Okay, in curling you wear two different shoes. Okay, you have a slider, so one foot is covered in like a Teflon coated surface, and the other surface is like a sticky rubber. Right? And that way you can push. You push with the gripper and you slide on the slider. Okay? And along you go. Right? You never want to step onto the ice slider first. If you do, you will do the whole flip over and look silly thing and then crack your head on the ice. It's not good. Okay? You always want to step down. Now, something we understand because we've lived in winter conditions our whole lives, we know what it means when ice is slippery. Okay? We also know how to walk. Okay? If we step onto really slippery ice, do we step like we would step on the floor? Right? Where we're leaning and there's directional forces. If we do that, we're gonna go over. Okay? So we know that when you step on ice, you make sure you have your weight right over your foot, right? So we set it on there and we make sure we're right over top of it, and then we take smaller steps, right? So that we keep our weight directly over top of our feet, because that increases the force of friction between our feet and the ice. If we lean any direction or the other, we'll have less force acting, and here's why. Friction is affected by not only the nature of the two surfaces, but how hard are they being pushed together. Okay? The harder you push two surfaces together, the more friction there will be. So if I have, let's say, a heavy object and a light object sitting on the same surface, the heavy object will experience more friction because it's going to push on the ground harder and the ground is going to push back harder. Right? Does that sort of make sense? Okay. In the wintertime, if you drive a pickup truck, do you throw weight in the back? Yeah, you should. Okay? Bags of sand, cinder blocks, hay bales, whatever. Okay? You should throw something in the back so that you have more weight over the back wheels. Right? Because more weight means your truck pushes on the ground harder and the ground pushes back. That increases the force of friction. You just make the truck heavier. Of course, that makes the truck less efficient because you're carrying around all that extra weight, but stopping and starting are kind of important. So that can help because we increase the normal force. So when it comes right down to it, you've got this formula on your formula sheet. The force of friction is mu times the normal force. Okay? And this is the same for both static and kinetic friction. The formula is the same. Okay? Mu is the coefficient of friction. That is, how sticky are the two surfaces when they're trying to slide past each other. Okay? Ice on Teflon would have a really low coefficient of friction because those two things would slide past each other very easily. Okay? If I was to put rubber and asphalt together, that would have a much higher coefficient of friction, which is of course why we use those two surfaces, okay, for driving purposes. Okay? Why the soles of your shoes are usually rubber. Okay? Rubber has a very high coefficient of friction against most other surfaces. Okay? Is that making some sense? Right? So in the wintertime, when we throw extra weight in our vehicle, we're making that number bigger. Okay? Which is of course going to increase the force of friction. The more normal force there is, the more friction there will be. How can we change mu? What are some things we do in the wintertime to make the surface have higher traction?
Salt.
Okay, so if we put salt on the road, that actually melts the ice, right? And it exposes the asphalt underneath. So the salt itself actually doesn't change anything other than it melts the ice so that you can access the asphalt underneath.
Studded tires.
Okay, studded tires, okay, or winter tires. And if you don't have studded tires, you get winter tires. How are winter tires different than summer tires? Anybody know the difference?
Tougher.
Isn't the material softer rubber?
Yeah.
It doesn't freeze as much.
Exactly. Winter tires are made out of a softer rubber compound, right? That allows them to remain pliable even at cold temperatures. And the more pliable your tire is, the better traction you're going to have. Okay? Summer tires tend to get quite hard at about 5 degrees Celsius and lower. Okay, that's why people start putting their winter tires on even before the snow flies. Okay, once you get down to an average high of about 5 degrees, you're better off to have the winter tires on because they'll provide better traction. The other thing is winter tires and summer tires have way different tread patterns. Okay, if you've ever noticed, like you look at what your winter tires look like in summer tires, when you're looking at the traction blocks, okay, that's like the tread pattern on a summer tire. You'll have the offsetting blocks. They'll have different shapes and stuff, but you'll just have the blocks. Okay, you might have the odd thing called a sipe. Okay, a sipe is a little like squiggly line. Okay, that might go across one of the traction blocks. On a winter tire, the traction blocks tend to be a little bit bigger. Okay, and they're offset in a different way as to channel water very quickly. And each block will have a lot of these little squiggly lines on it. Okay, the little squiggly lines are sipes. When your tire is sitting on the road, so normally we think of our tires as being quite round, but when they're sitting on the road, the bottom is a little flatter than the top. Okay, well, when you squish that, these sipes open. Okay, so when the tire sits flat on the ground, the sipe opens up. What that's designed to do is harness the polar nature of water, that whole hydrogen bonding thing. As the tire moves over ice, okay, that your tire melts because it's warmer, okay, or if it's spinning, it's melting the ice. Those sipes are designed to suck the water in and pull it away from the surface. Because if you have rubber, water, and ice, that is super slippery. Okay, we do not want that. That is the worst possible situation. So these sipes are designed to pull water in and throw it as the tire rotates, taking it away from the interface between the rubber and the ice, or whatever is under there. Okay, so they help to do that, and because they're made of a softer rubber, they can do that down to very cold temperatures, where your summer tires just become like a rock. Okay, now, things that can influence that, you need to have them properly inflated. Okay, if they're overinflated, those sipes are open all the time and they're not doing anything. Okay, if they're underinflated, then they don't open properly, okay, and they can remain closed and not do their job. So make sure you have them put on by somebody who knows what they're doing and puts the right pressure and everything inside. Okay, that sort of makes sense? Okay, so that would influence our ways we can influence mu. Okay, we change the tire compound, we change the nature of the tire, all of that. Okay, everybody good with that? All right, so we use friction very practically every day, and we do things instinctively that can make it more or less, whatever serves our advantage. Like, for example, if I want to move this desk, and because I'm old and have a bad back, I'm not going to pick it up and carry it, okay? If I just want to drag it, what's the best way to do that? To pick up a little bit of it and pull it this way, or to push on it and try and move it that way, which would be more efficient? Right, like, look, I'm putting all my weight on this thing and it isn't even moving, right? Am I working against myself by doing that? When I push on the desk, what force am I increasing? The normal force. It's not just the weight of the desk, now it's my weight too, okay? Now the floor is pushing even harder. Okay, so it's not gonna slide at all, but when I pick it up, I take a bunch of the weight off the floor. Now there's way less normal force, even if I'm not picking up all four legs, right? Just a little less weight on there is much easier than if I'm trying to push it with the whole weight on the floor. Does that sort of make sense? So little things like that that we do and we do it instinctively. We don't even think about it. It's just, oh, that's easier, and we do it. Okay? If you ever see somebody pushing it down the hall, they have very bad instincts. Okay? They should really just drag it. Yeah. Okay, so this is what I was showing you just a minute ago, right? If I push like this, if my applied force, right, looks like this, right? Yes, I've got a horizontal component there, but I also have the vertical component of my applied force added to the weight of the desk, right? That has to all be offset by the normal force. And if that's bigger, that's going to make more friction. Everybody with me there? All right. If I'm pushing this like this and the desk's not moving, what's the net force? 0. Okay, so this is my horizontal applied force. Let's say it's 100 newtons. What's the force of friction? 100 newtons. This would be a static friction situation. The desk's not moving, so I'm going against static friction. Static friction is always greater than kinetic friction. Once you get something sliding, it's easier. Okay? But kinetic friction's not as good at providing traction. So when you're trying to get up this hill out here, out of the parking lot, when it's really slippery, should you spin your tires really, really fast and gun it, or should you try and creep up the hill? Which is better? People are trying to think, I'm that guy that squeals my tires to try to go up the hill. Okay, you shouldn't spin your tires. If you're spinning your tires, that's kinetic friction. Your tires are sliding past the ice. Okay? All traction control systems, all wheel drive systems, they all want to minimize wheel spin and maximize static friction. Okay? This is why, if you've ever seen this, why like the Tesla can win drag race after drag race over the biggest, most monstrous masculine horsepower like race cars, because they spin their tires. No matter how good you are at launching that car, there's going to be wheel spin. Whereas an electric car diverts power and maintains, okay, the normal force and the static friction, maximizing its push forward. None of its energy is wasted on squealing the tires. Not that that doesn't look awesome, okay? Because I mean, there's just something about a car shrouded in tire smoke that just looks cool, okay? But it doesn't make you faster. Okay? A car that can maximize or minimize wheel spin is maximizing that static frictional force, and will get off the line quicker and accelerate better. Okay? Same with drifting. Okay? Drifting looks incredibly cool, but it isn't faster. You're using kinetic friction. Okay? It's why you don't see Formula One racers drift corners during a race. It's slower. Okay? You're better to keep those tires locked on the road so that you can maximize the engine power to accelerate. Once those wheels start to spin, you're wasting it. Okay, make sense? So next time you're spinning your tires, you gotta tell yourself, I gotta back off. And spinning my tires isn't gonna help. Okay? How many people here have a vehicle that has traction control? Okay? Most vehicles, even in the last 15 years or so, have it. Okay? Even if all they're doing is applying the brakes. Okay? You might feel this. If you hit it and you're on ice, you'll hear the tires and then you'll hear the anti-lock brakes clicking. You hear the tick, tick, and some of the wheels will lock up. Okay? The ones that are spinning, they'll apply the brakes on to send power to the ones that aren't. Okay? If you have true traction control, you have a thing called a limited slip differential, and it will actually cut off power to the spinning wheel and send it to the one that's got grip. Okay, it's called posi traction. And it'll increase your traction and thus your ability to move forward. Okay. All right, so this is a static friction situation. Like we said, static is always going to have more traction, more grip than kinetic. Okay? But once you overcome that static friction and the object starts to slide, then it's all kinetic, and it's usually much easier. Like, if I don't want to land on my face, because that sort of happened one time when I was doing this demo. Okay, if I'm pushing on this at a weird angle, and it all of a sudden I just happen to find like a slippery spot or whatever, and it just flies out, like it just goes, right? Okay? That kinetic friction is not going to be nearly as hard for me to overcome as the static friction was. Okay. Now, on here, okay, if we're talking about like angles and inclined planes, okay? We got mu times normal force. This is the odd situation where you might have to use that other side of the triangle, right? So this would be Fg, okay? This side, we've always said, this side's normal force, but we've never calculated it because we didn't need it, right? And then this side here is F parallel, right? If this is 20 degrees, okay? So let's say I put that 10 kilogram block on that ramp and it doesn't slide. What's the net force?
Very high.
The net force?
Zero.
Zero. The force of friction would be very high. Okay, so if it's not moving, the net force is zero, then that means that the force parallel and the force of static friction are the same. Okay, knowing that and this new formula here, calculate for me what the coefficient of friction would be between the box and the ramp. Okay, we know that mass, right? So we know this side, we can calculate that side. Okay, I'll give you a minute or two to see if you get it. Okay, so if we're looking at this situation here, okay, we can still calculate F parallel the way we always do. It's always the opposite side of the inclined plane triangle there, okay, where it's at the bottom. So I would go sine of 20 times 98.1. Okay, so sine of 20 times 98.1. All right, so F parallel is going to be 33.55 newtons. Okay, and obviously down the ramp. Now, F normal is the adjacent side to that 20-degree angle. So I just used trig to calculate it as well. It's just we've never needed to up until this question. So since it's adjacent, cos of 20 times 98.1. All right, so that side's 98.18. Okay. All right, so is that pretty, whoa, did I do something wrong there? Cos of 20. Sorry, 92.18, not 90. That seemed wrong because it was bigger. 92. Oh, come on. 92. Oh, you got me. Feels like a Monday. 92.18. Okay. So we've got 92.18 newtons worth of normal force. So that's how hard that box and the ramp are being pushed together, right? Since I know that F parallels the force down, the box isn't moving, is this also the force up? Okay, so this is also then the force of friction. Right? If the net force is 0, the force down and the force up the ramp have to be equal but opposite. Okay, so if I'm looking at this formula here, I now know the force of friction, it's 33.55, and I know the normal force, it's 92.18. Okay, so mu will be the force of friction divided by the normal force. Okay, so 33.55 divided by 92.18. Okay, so I get a decimal. Is that okay? The coefficient of friction basically tells you what percentage of the normal force is actually turning into friction. Okay? That sort of makes sense? Or sorry, what amount of the frictional force, sorry, is turning into friction. So what we're doing here when we take that is essentially we're just getting a percentage. What percentage of the normal force is friction giving us? If the coefficient of friction was 1, then obviously they'd be the same number. And 100% of that normal force is turning into friction. Okay? That's like basically never the case, but okay, you get the idea here. Everyone follow me there? Now, what are the units for that? I just divided the force of friction by the normal force. I just divided newtons by newtons. What do I get?
Squared.
That'd be if I multiplied them. Nothing. It's a coefficient. It doesn't have any units. Okay? It's just the percentage, basically, of the force of friction, of the normal force that is becoming friction. In this case, it would be about 36%. Okay? Everybody with me there? All right. Now, we're looking at this. We sometimes do a lab on this when we have time. Obviously, this semester we're not going to have time. Okay? But we take these mass sets that we were using before. We actually put little rubber grippy things on the bottom of them. Okay? And then we put them on an inclined plane. And we just tilt the incline until they start to slide. Okay? So up until that moment of sliding, what's the net force? 0. That means the parallel force and the force of friction are the same. Okay, now there's not very much weight in there, so I got this pretty steep. Okay, as I put more weight in there, well, let's not put the video in yet. Okay, if I put more weight in there, should anything change?
Accelerate faster.
Maybe. Right? If I increase the weight, am I also increasing the normal force? Okay. But I'm also increasing what other force that's going to be involved here if I increase the weight? The force parallel. Okay? So you don't end up getting the results you think you would get. Okay? So that's starting to slide right now. I don't have this as steep as I did on the last one. Okay? The more force I add, and there's a weird thing that goes on there, okay, where you don't always get a consistent kind of relationship, like that's steeper than the first one. Okay, it's weird, but when you do the calculations there, you actually do find that that there's a linear relationship between normal force and the force of friction. That linear relationship is this number. No matter how much weight I put in that box, mu is always the same. Would you agree? Because mu is how sticky is this rubber pad and the wood when placed together. Okay? All right, everybody okay with those ideas? Okay, so the big thing we got to get out of today is this. There's two kinds of friction. Static friction, where our net force would be 0. Okay? And kinetic friction, where there will probably be a net force. Okay? And then we also have to remember that normal force and mu affect friction. So the harder two surfaces are pushed together, the more friction there will be. The bigger mu is, the greater friction will be. Okay, everybody okay with those ideas? Okay, that's kind of the big thing we got to get out of this. Okay, let's give that one a try. So this time I give you mu. So the coefficient of friction in this situation is 0.125. I am pushing the box up the ramp, okay, with 120 newtons worth of, no, that's not right. Gotta make that force bigger. That won't work. Oh, yes it will. Yeah, I'm pushing it up with 120 newtons worth of force. Calculate the acceleration of the box.